morning. I'm Eric. Chris is here at the audience, so maybe I will have some questions that he might be interested in answering. So first, very quick thing about we're going to talk a little bit more about traditional tech of how to build multiplayer games. So why are we here in a cloud-based session? So this actually makes a lot of sense. It's related to the question I asked about how do you communicate between servers, because you don't want to add more latency knowing that your engine does a lot of latency and your controller in your TV do a lot of latency. So cloud gaming is not the problem in here, but you still have the latency problem. So you don't want to add any more latency on top of that. So this is one thing that might help a lot in that, and I hope that will be clear. And last thing is, before we start, is although we do have products about this tech, etc., this talk is not about the product, it's about the ideas and the tech. So please ask any question you have. We'll be happy to answer. So just like cloud gaming, determinism seems to be like a game developer's dream. So you focus on doing only the gameplay code. You don't think about network. You just think about, OK, I have a computer. There are many controllers because there are many players, but you don't have to think of them as being from different computers. This is the premise that you can, this is the thing that you can achieve with determinism. So it sounds like a dream, as I describe it. Why aren't everybody using this? Why isn't everybody using this right now? So then reality kicks in, and here is the thing. It's very hard to accomplish determinism. It's difficult to implement these things. And especially the most known implementation of determinism, which is the traditional Lockstep model, is very limited. It has a lot of issues, including a lot of latency. So this is clearly not very useful anymore, although it has been very successful in the past. And last thing is you still use engines to build the games, and engines are not built to be deterministic. Neither of them are built to be deterministic like this. So let's dig a little bit deeper. First, by understanding a little bit about the history of this. So by deterministic architecture, like a pure deterministic architecture, what we mean is that the clients, either them being different servers in cloud gaming or the real clients in traditional sense, the idea is that they only exchange input with very, very low bandwidth requirements, and they do simulate tick by tick based on the complete input set. And if you use deterministic algorithms and data structures, at the end you're going to have the same game state at the end of 10,000 frames. So it's a very simple premise. But in the practical approach, number one, which is traditional Lockstep, has been here for 30 years with a lot of success, especially on the RTS genre. For example, StarCraft 2 still runs a pure Lockstep model. But it has a lot of issues. First one is that you have to apply input delay because you cannot fake the speed of light, and you have to wait for the inputs from the other clients to, let's say, be able to simulate exactly like the other client. So clients have to exchange input. So what you do normally is you apply input delay before you can actually simulate a frame. That's clearly not good. And it also all breaks down if one of the clients starts to run slow, or if it has high latency, especially ping spikes, which is pretty difficult to handle in those old times. Then let's move forward, and let's bring us to 2018 or post-2010. So the idea here, first one, is let's get rid of Lockstep completely. So maybe some of you guys have heard about GGPO and what it did for fighting games and all that. So the idea here is that you don't have to wait for the other guy's input anymore. As long as you have the input for the local player, you just simulate that tick. So you go back to, let's say, a single-player experience with zero lag. Well, not zero, the controller, the TV input, lag, etc. But you get to the same experience as single player. And what you do with the remote players, you just do a very, very simple heuristic prediction of what he's going to do. If he's going left, he tends to keep going left for at least 20 ticks, running at 60 hertz, for example. And what you do is when eventually the input arrives, you can roll back the entire game state and resimulate to fix the mispredictions. But normally these mispredictions are only for the remote players, not for the local one. So the local one doesn't change anything, and you just have the single player like zero latency experience. But then this is what you could do when GGPO was still, let's say, available. But it only worked for 1v1 fighting games, for example. It was used on Street Fighter V and latest Mortal Kombat. But then there are a few tricky things if you want to do this for 3, 4, 10, 30 players games or more. And then you have to have a server in the middle to coordinate input exchange and take care of keeping the actual game instances completely in sync in terms of clock, because hardware clocks drift. You also need to manage what to do when there are latency spikes. Even thinking about running this between 2 servers, you want to have players in the US with the last mile server playing against players in Europe. In Amsterdam, the server is running. You still have to communicate between these 2 servers, and there might be some issues between those. So here's the thing here is that to do stuff in this, the stuff that you need to do to achieve non-lockstep predict rollback determinism requires a server in the middle that coordinates the input exchange. And this is something that you normally don't find on the internet forums. There is not much information about it. But then let's just dig a little bit more on the actual challenges here. So essentially, you need a new game engine to run this. You need to run different math because floating point math is not deterministic. So you need a complete library for that. You need new physics because the null physics engine that you get out of the box is deterministic. You need same for pathfinding, same for if you want a tight control of animation. So just a little bit of a teaser. This is exactly what we do. We have everything in-house because we needed to have this. But the good news is you can do that. It's not impossible. And then the real challenge is how to achieve this near zero latency experience with rollbacks. And here's the real challenge, which is how to do this very, very fast. How can you actually save and restore the game state to a previous version? And whatever is the architecture you use for the frame buffers, etc., you end up having to do this. You end up having to do a deep copy of your game state. So this is just a quick example of what that means. If you have an object A that references an object B, if you do a simple copy of a clone of object A, you still keep the reference for object B. This is not what we need. We need to do a deep copy, which is we need to copy the whole contents to another part of memory, for example. That's the only way to do rollbacks. And how can you do this really, really fast? So just to cut the story short, I'll just show you some numbers of an experiment I ran. So if you are very naive, you can try to just serialize and deserialize the game state. But then this is like 100K instances of an object that has 4 other inner objects of 2 different types. So a serializer will be like 3 seconds to do the whole thing, so it's pretty bad, clearly. If you do a manual implementation of a deep copy, which is what some, let's say, Stack Overflow forums recommend you to do, you get down to 100 milliseconds to do the rollback. It's still not good enough. But then let's not use objects and classes anymore. Let's just use whatever is your language of choice. Let's use plain value-based structs that you can just clearly copy without using the heap. So if in C#, this was running C#. So if you use just a struct array and you do an array copy of this, you get down to 5 milliseconds. And finally, if you decide to do just a native mem copy, of course, it's going to be better. So it's 1 millisecond. And you can understand what was the choice we did in terms of what to do for rollback. So basically, please do mem copy if you're going to implement that. Anything else is going to be too slow. So in summary, these are the design choices, the technical choices we did, which is basically keep game state as a memory-aligned block of structs, whatever the language you choose, and use native mem copy for rollbacks, and old-fashioned pointers, inline everything. So math library, we're talking about fixed point, not floating point. So inline everything. Don't think about anything else. It doesn't help. And of course, never allocate anything at runtime. That's regardless of what you use. So in terms of API designs, we chose, this is about product we have. So we never expose networking code, just like cloud. You don't think about the game as networked. You just write forward simulation as if you had more local players. We try to protect common pitfalls with pointers. Even if you're doing this in-house, you have to try to achieve this so new developers don't fall into the normal pitfalls. And just a quick thing about multi-threading. Our internal idea now is that we're exploiting this a lot internally, but we're not exposing this to the developer too much. We think it's it may actually add more overhead because many of the tasks you actually do in gameplay, not in rendering, in gameplay, are inherently sequential. You're modifying data that depends on another modification of data, etc. So if you try to do that multi-threading, you're just adding overhead in most cases. So we do exploit it internally, but we're trying not to expose too much. So that was my summary in the time we have here. I have time for questions, I think.
So yes, we do have time for questions. People are so serious. Come on, guys. I know the party yesterday was hard, but you can do it. And you know more technical things than I do. I could try to be smart and try to ask
We have
questions.
one here.
Good, thank you. And my technical knowledge doesn't go that
Very interesting. So do you provide developers some sort of libraries that takes really care of all that, and how easy it is to use, and where can you get it?
Yeah, that's, as I said, I was not talking about the product, but the ideas behind it. Yeah. But we do have a product called Photon Quantum that is exactly all that. We do have the physics engines, 2D, 3D, NavMesh agent. It's completely decoupled from the rendering engine, so it's agnostic to that as well. And it's from Exit Games Photon. We can just talk. And
yeah. So people with custom game engines or using different engines, they could be utilizing your synchronization.
Exactly. Yeah. Exactly, because it's not tied to any particular engine. Although we do have a pretty good integration with Unity, it's not at all. I mean, the simulation is completely decoupled. You write it in a separate Visual Studio solution that does not even know the engine exists. So it's just pure simulation.
Right. Yeah. Are there any requirements for the engine? Like you mentioned, like you need to basically have a flat array of memory, like what you can mem copy. So like, is that a requirement or?
We have flexibility for you to add custom stuff on the game state if you want to do in an advanced way. Yeah. Actually, we have several layers. You can even not use our default approach, which uses the memory align based structs. For this one, we have a custom ECS where we have a DSL for you to define the data structures, and these get converted into pure memory-aligned blocks. But you can actually do everything custom if you want.
All right.